Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number. The climate system is a dynamic and complicated process. Many years ago, I spoke to a researcher who informed me that they had developed a fantastic predictive tool that could give very accurate forecasts for 8 hours into the future. The problem was, it took them over 200 hours to finish the computation. Now, certainly computation has gotten a lot faster in the intervening years, and the resulting forecasts have presumably gotten a little better, or at least quicker, but there's no free lunch when it comes to predicting a complicated system. Unless, under certain conditions, maybe there are some deeply discounted lunches. We all know the traveling salesman problem is hard to solve. But if you lived in a country with just one highway that goes in a circle, solutions turn out to be pretty easy when constrained in just the right way. Today on the show, I speak with Elizabeth Barnes about the paper Identifying Opportunities for Skillful Weather Prediction with Interpretable Neural Networks.
So my name is Elizabeth Barnes. I go by Libby, and I'm an associate professor in the Department of Atmospheric Science here at Colorado State University.
Can you tell me a little bit, broadly speaking, about your interests research-wise and things like that?
I guess in broad terms, I'm a climate scientist. I've been studying climate dynamics. That includes climate change, but also the Earth's climate as it is today, as it was in the past. And really probably why I'm on this podcast, but also my broad interests are in the data science side. So how do we use data and analysis tools, be it statistics, mathematics, modeling, to understand the Earth system and all of the interacting pieces?
Could you go into a little depth about the data you are interested in and even what's available? As most, I think, listeners who do some data science, maybe they're used to working on the internet where it's as easy as just tracking something, but the Earth has been leaving us clues for a while. What do you have access to study?
Specifically, the part of atmospheric science that I study, I like to say we actually really have data coming out our ears. We have so much data. Now, it's not all good data, but one of the reasons I'm so excited about data science and machine learning techniques is how can we utilize the data that we have, even when some of it maybe isn't perfect. For example, we have in earth science or in climate science, we have paleo records, so ice cores that tell us what the climate looked like, hundreds of thousands of years ago. We have today satellites that are constantly either orbiting the Earth or sitting still and staring at one place over and over again, and they're pouring data in all of the time. Sometimes it's hard to just get the data and process it. Once we have it, then, so we can do the fun stuff. Just getting it into a processed form is a lot of work. We have climate model data. So we have these big climate models that are being run on supercomputers all over the world to try to help us understand the climate system. And they are outputting a lot of data. And people need to look at it to try to, answer and ask interesting questions about the Earth system. And then we have people here in my department. I don't do this, but, atmospheric scientists going out, say, with a weather balloon or a radar and actually measuring, thinking about the weather and the climate state right where you are. So there's data coming from all over the place. It's not as easy as just tracking something on the internet, however, and often it's just because the sheer amount and volume of data is so hard to deal with.
When I think of a lot of the physical sciences, and I have limited an introduction to atmospheric science and things like that, but what I'm always struck with is strong underlying models that people have put together over decades or centuries maybe, and then it's a very sort of analytical process, which is almost antithetical to machine learning in a way, where we just kind of take the data and let the model kind of emerge from it. Is there a dichotomy in your field, or is it just a blending of both approaches?
So I think a few years ago, when I would say the phrase machine learning, a lot of people in my community saw them, as you just said, as the physics as totally separate from these data science tools. And they look at me saying, I'm a scientist to actually understand why these tools aren't going to help me. In my view, though, there's no issue whatsoever. To me, the whole idea is how do we understand the data to try and inform sort of those rules of physics that we think we know or come up with new ones. And vice versa, if we think we know what those mechanisms of that physics is, how can we test it? And oftentimes at the scales I study in climate science, we're not talking about, a few meters square. I'm thinking about half of the globe. I study hemispheres. I can't just go out and take one measurement and get that. So I need to learn to extract information from the data I have coming in. So to me, this is the exciting part, is actually showing that we can merge the physics and the machine learning to be better scientists.
And what are some of the interesting questions you're asking about the Earth system?
One of the interesting ones right now that I have quite a few people in my group thinking about is predictability. So if you're familiar with the butterfly effect or chaos theory, that derives quite a bit of what we do. And this is the concept that even if you know the state of the Earth relatively well, you'll never know it perfectly. And at some point, those tiny errors are going to grow and grow and grow until predicting anything will be nearly impossible. I tell students this is a lot like, you want to know what the weather is going to be in a few days, say you're going on a camping trip. If it's just out for Thursday, you might pick up your phone and look at what the temperature will be. But if you were trying to plan a party in 3 months' time, you would never pick up your phone to try to figure out exactly what time of day you should have your party, whether it will rain or not. And this is that idea of chaos coming in. So I think in some ways, our field is set up for an impossible task. We were supposed to make all these predictions, but we sort of know already we're going to fail. So the question is, when can we make predictions that are good? And when do we know they'll be bad and we just shouldn't bother? And why can we make good predictions sometimes and not others? And so to me, one of the big questions is, how can we explore certain states of predictability of the Earth system and understand when they're going to appear and when they vanish? And how can, again, we make that into usable information that society wants to take and use?
I think you described that as the forecasts of opportunity in some of the published work. Is that right?
That's right.
Yeah, so let's dive into that a little bit. What about certain times makes them more amenable to prediction than others?
So we know already that there are particular states of the climate system that may lead to more predictable behavior than others. And an example that we study quite a bit falls under the fancy word of a teleconnection. And if you want to, you can sort of picture action at a distance type things. It's really not. It's all good old-fashioned physics. But a good example of this is when there are big storms in the tropics. The word for this phenomenon is known as the Madden-Julian oscillation, but these big storms that start in the Indian Ocean and slowly move east over the course of about 30 to 60 days. Those storms act sort of like a rock thrown into a pond, and they send ripples out into the northern and southern hemispheres. And those ripples take about 2 weeks or so to reach North America. And when they reach North America, they change the pressure systems and actually allow us to know where storms are going to be headed. Now, without those ripples, without that rock in the tropics, the storms are much less predictable than when we have the sort of ripple effect steering those storms into known locations. So that's a great example of how we use this concept of forecasts of opportunity or opportunities to make skillful forecasts.
When you're hitting some sort of limit, maybe it's that 2-week limit or even outside the forecast of opportunity, what is or maybe I'm not even sure if this is insightful, but do we have an understanding of what the ceiling is? Is it that computers aren't fast enough or we don't have enough observations? What's stopping us from going 4 weeks out or 20 weeks out?
First of all, we don't know how far out we can go, really. This is one of the exciting things about a particular area of research right now called subseasonal prediction. So thinking back even 5 years, you probably had heard at the time about weather prediction. You can't really get away from talking about the weather and what the forecast will be. And on long time scales, and so we're thinking maybe on a year time scale, if you've ever heard of El Nino or La Nina, these are states of the climate system that sometimes give us an inkling of what might happen in the next year. But what about those time periods in the middle? And people have been studying it for decades, but it wasn't until the last 5 years or so that a huge international effort has been put forth to try and investigate those timescales and ask the question that you just did, which is, can we make predictions on that timescale at all? And the answer is, excitingly, sometimes, which is great. Now, theoretically, you might be wondering, what sets that timescale that we can make predictions? And as I mentioned, chaos really sets that how far out we can go for these errors in our initial conditions or what we think the state of the system looks like right now. And many people actually don't realize it, but they're familiar with what that time scale is. And it's really about 10 days. After about 10 days, whatever weather forecast you've been following, you probably don't really believe, right? You don't really trust it until you're only a few days out. And that's really that time scale when chaos takes over.
And I think the science alone is a reason enough to have inquiry in this area, but I'm curious if you have any thoughts about more practical use cases. Are there industries or governments that need this sort of forecast and depend on it to make decisions?
Yeah, absolutely. That's one of the reasons this sub-seasonal timescale and longer has become such a big interest is there are a lot of people that say we need this timescale for planning. So emergency managers actually need to know the general regions that maybe extreme weather might occur a few weeks in advance so they can fly in all the materials. And then it isn't until the day or two before the extreme weather event that they actually then, put all those materials on trucks and drive them out to where they think they'll be needed. So that's an example of reservoir operations. So if you're familiar a few years ago with the Oroville Dam disaster, this is a case where, reservoir managers are having to decide, do we let water out because more storms are coming in a few weeks, or do we keep water in because we're headed potentially into a month of no rain? And so this timescale is this 2, 3, 4 week timescales when they're having to make these really important decisions and have, need the information to make informed decisions. It's not like a weather forecast though, where, someone will say it will rain in 3 weeks and 2 hours, but they might say, the odds of it raining a lot in the next 2 weeks are high or low. So yeah, there's a lot of need in society. Certainly businesses thinking about certain trading and futures trading happens on these timescales. Farming, and so agriculture, they think about, in springtime, are we going to get another frost or is this the end in the next few weeks? Should I plant or should I wait? So there are a lot of sectors that are interested in this information.
Well, the paper that I first got brought to my attention that introduced me to your lab and collaborators and what was going on there is the paper titled Identifying Opportunities for Skillful Weather Predictions in Interpretable Neural Networks. So we've got a couple of things to unpack. Maybe to start with, could you describe the general problem that you were going to pose to a neural network?
Yeah, so this is very nicely full circle back to this idea of skillful forecast of opportunity. And so that's really what this identifying opportunities for skillful weather prediction comes down to. And the thinking here is, I guess, what makes this interesting to me and different than what I've seen in the past is that a lot of neural network or machine learning tasks are often framed in the sense that with enough data or enough time or the right, machine learning algorithm, we should be able to get the correct answer all of the time. Just think about something like trying to label whether there's a cat or a dog in an image. Every image either does or does not have a cat. And so the concept is if we do a perfect job training our model, we're going to get it right. But this is where, again, we come back to this concept that on the timescales we're talking about with weather and climate prediction, we will never get it 100% right, ever. Chaos sort of tells us it's not going to happen, as does the complexity of the Earth system. And so the concept of this paper was, maybe we can use neural networks instead of trying to get the right answer all the time. Maybe we can use them more intelligently to help us identify when we should even be trying to make a prediction in the first place. So that was the concept behind this paper.
That's interesting. So identifying those conditions you were describing where there's an understood correlation or connection between points and the settings are just right where you can make a prediction under circumstances. Is that the core idea?
That's exactly it. And I should say sort of the old-fashioned way, still the tried and true way, don't get me wrong, it's great, of doing this with climate scientists sitting down, thinking about the physics of the Earth system and sitting there with their equations and thinking through how might these different pieces of the atmosphere, ocean, land surface, sea ice interact. And that's how we would try to identify these forecasts of opportunity. The concept here is, well, this is sort of what neural networks are good at. They're good at looking for relationships amidst a sea of noise. Maybe they can help us identify some of these opportunities we never knew existed.
So then how do you formalize that as an input to the training data set? Is it comparable to what's done in computer vision, where kind of one pixel becomes one feature?
Sort of, yes. That is in some ways what we're doing. So we might input a single, say, map of what the ocean looks like today. You might input lots of different variables, right? Just like in computer vision, you might input multiple images rather than just one if you're trying to make some sort of prediction. So in this case, we use every pixel is sort of one input of this map of the world or of this data of the way this climate system is right now. And then the goal is the output is to predict something into the future. So say whether it's going to be cold or warm I'm in Fort Collins, Colorado. So whether it's going to be cold or warm over Fort Collins, Colorado in 2 weeks. And so that's how we've set up the problem to see, what features of our input, what features of today's weather and climate can inform us about 2 weeks from now.
And could you describe some of the details of the neural network's architecture, how you put this together to go from inputs to that final output mapping?
Yeah, we're still playing with this. So we've started quite simple. So computer scientists who know what they're doing might think, well, there are way more complicated ways to do this. And I appreciate that. But part of what we're trying to do here is also understand how that prediction is made. The goal is not just to make a prediction, but the goal is to understand why that particular state might be more predictable than others. And because of that, we decided to start really simple. So in this particular paper, we're actually using what's called a feed-forward neural network. So a very standard neural network, sort of, if you will, the vanilla flavor, where we just have, in this case, in this paper, we have just 2 layers with 8 hidden units in each layer. In this case, we do classification. So 2 output nodes. We're just predicting higher temperatures or lower temperatures than normal. So we've truly set it up to be incredibly simple, the hope being that we can train it to do something. I will point out, I have many members in my group and now quite a few papers using more complex architectures and more complex outputs as well. But in this paper, we wanted to start simple.
Thanks to this week's sponsor, Oval Edge. Oval Edge is a cost-effective data catalog designed for end-to-end data governance, privacy compliance, and fast, trustworthy analytics. Our end-to-end data governance suite has flexible solutions at a fraction of what other providers charge, starting at $100 per user per month. If your company hasn't addressed compliance yet, you need to get on that right away. If they have, it's always important to double-check that you have the state-of-the-art and the best possible solutions. One of the reasons a lot of companies delay solving these important issues is because they don't really know what to do with their personally identifiable information, or PII. You need it to operate your business, but you owe it to your customers to protect them. But you don't have to do that alone. Oval Edge uses AI to crawl all of your systems. They have a suite of data classification features that can help build your data catalog in an automated fashion. And that's not just your standard run-of-the-mill databases, but it's also BI platforms and ETL tools and data lakes. Anywhere your data lives, they can help. Download their Implementing Data Governance Guide and schedule a demo by visiting ovaledge.com/dataskeptic. That's ovaledge, ovaledge.com/dataskeptic. And with the problem set up, before you went into it, what kind of expectations did you have about the degree to which a neural network could actually make a prediction under these circumstances?
So this is why I really love doing this as a scientist, because I actually have a feeling for, what we should find and when and how. But then the cool thing is maybe the neural network will show me I'm wrong. Or maybe show me I'm right. That can be nice too, right? So in this case, actually, there weren't really any surprises. We knew that there would be some states that were more predictable than others, and we knew it should learn something or we've messed something up. And we knew that because there are decades of papers written on this topic of how to use the state of the ocean to understand what might happen in the coming months ahead. So because of that, we sort of knew we were setting ourselves up for success in that sense. And indeed, it did okay.
Yeah, how do you end up measuring it? Is it with the typical data science tools of accuracy or F1 score or things like that?
Yeah, that's what we're using in this case. I will point out a lot of problems in earth science are actually what we call regression tasks. That is, you want to predict a number, a continuous value, say from -10 to 10, and anything in between. But a lot of machine learning algorithms and methods have been set up for classification tasks. That is it a cat, a dog, a cow? A spoon. And so because of that, again, we started with a classification task, but I just want to point out that a lot of work that we're doing is really saying, how can we take these and turn them into regression tasks, in which case it's harder to come up with some of these metrics, right, of how to evaluate it. But for classification, you're right, there are a lot of pretty standard approaches out there, like accuracy, which is the one we did. However, the thing that makes this interesting, and maybe we're getting there, but I'll jump in now, it's not just the accuracy of the whole model. Now, if you look over all of the testing data, our accuracy is actually not great. I mean, it's something like 60% accuracy. And you might think, well, that's not very exciting.
Well, what is random chance? Is it 50-50?
Good question. Yes. So we have two outputs and we've made sure that there's the same number in each. So the random chance is 50%. Now, 60% is above the noise, but still you might be a little underwhelmed here. However, our goal, if you recall, is not to try and make predictions all the time. Our goal is to try to find when we have predictability. And so we actually use the neural network's output or its confidence in this classification task to try to assess when the network is more confident, is it more often right? And the answer is that makes this interesting is yes. So in the top, say, 20% most confident predictions, the network actually, its accuracy is up closer to, 80 or 90% accurate.
Interesting. So it not only has learned something about the system, but it also seems to have learned when it's capable of making a good prediction or not.
You got it.
Well, one criticism some people have of neural network approaches is that they're just a black box, that how do we know you haven't just overfit your data or something like that? We can't tell how it's working. How does that play out in your use case?
That's step 2 in what we do. So step 1 is first set up the problem so we can actually learn something with the neural network, or the network can learn. And we've done that, right? So it's accurate above random chance. But how is it making this predictions? What particular states are more predictable, and how is it using that information? And again, we're not just asking this from a trust perspective. We're actually asking this first. We do want to trust our network, don't get me wrong, but we also want to learn new science. And so for that, we've found that explainable AI tools can be really helpful in not just developing that trust that our network isn't, garbage in, garbage out, or overfitting, as you pointed out, but that it's actually learning the physics, or at least the connections and relationships that are really there. And so to do that, once we've trained our network, we use a particular explainable AI tool, there are many, to then track the predictions back through the network to assess which parts of the input are most relevant to that output. That is, when the network gets the prediction right, where was it putting its emphasis or its focus on those input fields? And in doing that, we can actually make maps of the parts of the sea surface that are most important or lead to predictable behavior elsewhere in the coming months.
And then in what way does that become perhaps actionable? Do we deploy more sensors or pay more attention to that area?
So I think at the moment, I would say that's still a few steps ahead. I think the first step is we need to identify these potential, and I say potential, with emphasis here, the potential sources of predictability identified by this neural network. But then as scientists, we need to go and do a bit more than that. We need to ensure that they make sense, that there's physics behind them before we start taking action. And so the step 2, it's not in this paper, but sort of implied in the scientific community, is that we start exploring these different patterns of, say, the ocean surface and trying to understand sort of the mechanisms in the F equals ma kind of way, bring out our equations and our paper and pencil and make sure that they make physical sense. And this is important because even if you generally trust your neural network, and even if you're using it the way you're supposed to, at the end of the day, we don't have an infinite amount of data. And so spurious correlations or relationships certainly show up. And so the only way, in my view, to really get at those, since we can't just go out to another Earth and collect more data if we run out here, right? We have to actually come up with a theory behind it. I will also point one of the other things that makes this tricky with our data set is you might think, well, we've had satellites up for decades. Why don't you have enough data? I will point out that the climate system is changing rapidly. So if you just think about it in the statistical sense, we don't have 30 or 40 years of a data set. We actually only have snippets of different data sets as the statistics of our climate changes. And within all of this prediction work, we have to work in, could the warming of the climate be interfering with the signals we're looking at or changing them?
Gotcha. Yeah, that's an intimidating thing to think about, I guess, that all the work could change as the dynamics of the system evolve from climate change. Is that something that's just kind of invisible to us? Or could, smart researchers kind of anticipate where temperature is going and build some good modeling for that? So what's possible here?
Yeah, so this is an area I'm really excited about. which is, it put it well at the beginning of that question, which is, well, it's sort of scary to think all of the work we're doing now may not be applicable in even a few decades because the climate system's changing. That's something that's on my mind, honestly, every day. Or maybe the other way, maybe the sources of predictability in the future aren't present right now. Maybe things will become more predictable, which would be good in terms of, predicting the weather. I mean, certainly it's bad why it might become more predictable because of climate change. But ultimately, these are really interesting questions that I think scientists are thinking about. And one way to do that is we actually utilize climate models. So what we can do is take a climate model, which is a incredibly complex, dynamical model is what we call it, that's been integrated to include things like greenhouse gas concentrations, anthropogenic aerosol emissions, the ozone depletion and recovery. All of these are inside this one climate model that's also simulating the oceans, the ice, land ice and sea ice, the Earth's surface, the atmosphere. And in doing so, we actually have a lot of this data that we can sort of, play with, sort of like a sandbox to test out some of our ideas. So what we do is we will train, say, a neural network to make predictions on over the 20th century, like the data we actually have in observations. And then we will use those same statistical prediction models to try to make predictions in the future in this climate model and see if they work or not. This might be the first sort of indication of whether the system is going to leave where it is in terms of its predictability or whether it will be about the same. And these are the types of tests we're doing right now.
One of the features of the paper that stood out to me as very interesting was the interpretability aspects, that you're able to, as you were describing, map back from the neural network to these importance areas. Did you have any opportunity to put that in front of a domain expert who could interpret that and say, oh, it seems the machine is doing something clever, or it's just kind of listening to noise?
This domain expertise, that's again why I think this is so exciting doing this as a scientist, is I'm trained in that. So I actually get to play, wear both hats and play both sides. So yes, many of these patterns we are finding do make sense. For example, one of the patterns that the neural network's picking out is the El Nino or La Nina signal. And we know that El Nino and La Nina can lead to predictable behavior in, say, temperature over North America. So that was great indication that it's learning something physical and real and not just, the noise. On the other hand, it also has picked up on features. We didn't show them as clearly in this paper, but in other work, features near Japan that have been theorized to potentially be important for temperature prediction over North America on monthly timescales. But if the neural network's also picking it up, it makes us think maybe we should look into this more. So the hope is, at least the way I've been treating this approach, is the hope is once in a while the neural network does something that makes sense, right? Something that we expected already. And that gives us a little bit of trust in what it's doing to then go and explore some of the mechanisms maybe we hadn't thought as much about that it identified as important.
Could you talk a little bit about the relationship or the challenges around bringing together these ideas of, deep learning that come from predominantly computer science and other fields that may not have the same overlap? It seems like you have a multidisciplinary group put together. What's it like to bring all these talents into one roof?
When I started off in machine learning about 4 years ago, some of my closest collaborators were, as you said, a computer scientist and a data scientist to really learn these tools and how they talk about them. Interestingly, though, and in recent years, most of the people I work with these days actually are trained as domain scientists. And I certainly collaborate with computer scientists, but I have found that often the trickiest part is not the writing the neural network code or getting the data processed. It's actually interpreting the results and doing something useful with them. For me, that's the hard part. And because of that, it's been best to work with others who have also been studying the climate system so we can sort of put our heads together to understand what the process is and what's actually happening. With that said, in order to learn these tools and learn how to use them and know what's cutting edge right now, I've certainly haven't had many collaborations with people outside of the climate community. Why I think that has worked so well is in many ways, geoscientists are already trained as data scientists. It's sort of what we do already, just without the title. And certainly we don't know all the tools that someone trained in data science does, but we understand generally many of the pitfalls that can happen, the importance of how you process your data before you ever put it into one of these, statistical or machine learning models, et cetera. Because of that, I think pretty quickly we've been able to find some common ground for discussions. And so because of that, I think this has been quite honestly comfortable of a collaboration.
Well, can you tell me a little bit about, broadly speaking, how machine learning gets applied? I know this is one example. Are there other ways in which your field is taking advantage of these tools?
Yeah, so there are so many groups and people thinking about how to use these tools for geoscience or climate science or, something with the Earth system. Some of my favorites include colleagues that are using it to actually explore the driving dynamical equations of the ocean. That is, as you started this podcast, Kyle, you think of these two things as separate. Physics is sort of separate than machine learning, but they're actually using machine learning to try and learn the equations of motion, which are pretty amazing. And indeed, they're doing it successfully. So that's one of my favorite applications. Another big area in my field is, I mentioned climate modeling, well, also weather modeling. Many of these models have a lot of complexities and relationships that scientists had to try and figure out in the lab or theoretically to put into these models to simulate, for example, cloud processes, something incredibly challenging. And a big area of research right now is, can we use machine learning to learn those relationships better? So when we put them into the climate model does a better job at simulating clouds. So this is a huge area of research called cloud parameterizations with machine learning. Some people are exploring peer prediction with machine learning. So saying, what happens if we replace our weather models, which we see, on the news, on the Weather Channel every day? What if we replace those models with a purely machine learning model? How does it do? One with no physics whatsoever. And believe it or not, it actually does okay. Doesn't beat out our physical models, which honestly makes me feel good. It says that physics does indeed matter, but they do okay. So then you start to get to be creative and say, well, what does this mean? We may not do as good of a job at forecasting the weather, but we're doing it faster. We're doing it more cheaply. Can we still use the output to help inform our ultimate, say, predictions about what's going to happen? So how can we do that intelligently? Another application, as I've mentioned, is generally using these tools to learn new science. I talked about it in terms of predictability, but there are other colleagues out there trying to set up these machine learning algorithms so the output is not the prediction, the output is the science that is learned. And finally, the big one, which is sometimes called physics-guided machine learning or knowledge-guided machine learning. It might bother you, it certainly bothers me, that we have hundreds of years of physics and that sometimes it feels like we're throwing them out the window to just embrace these machine learning tools. So a big area of research is, how can we include the physics in the machine learning architecture or methodology itself? How can we truly blend these two things to sort of get the best of both worlds? So I think this is an incredibly exciting time for people studying the Earth system to use these tools to really wring out all of that data that we have and learn more about the mysteries, I guess, of the Earth.
Well, this seems to be a growing field, not just in the sense that the science is moving along, but it's important to industry. And with climate change going on, it seems to me, I'm an outsider in this, but we're going to have to start making big long-term decisions about how to address it and maybe change agriculture and all this kind of stuff. Certainly an area for a young scientist to be finding their way in and taking a specialization. Do you have any advice for undergrads or people like that who are curious about this field? Where should they go to get started?
The advice I tend to give, at least for the type of work my group does, it's best to go out there and really get a degree in a science, in the physical processes or economics or the thing you're interested in. And then once you understand that deeply, applying these tools to that data, you can really think then about machine learning and AI as sort of a hammer in your toolbox. You should have many tools, and this is one of them. I find that is the way, at least for science, that we've been able to make the progress that we do, is having people who understand the data applying some of these methods. Sometimes students feel like they need to go out and get 2 degrees, right? They need to be an expert in machine learning and be an expert in the domain science. And of course, yes, that would be great. But if you don't have the time to do that, I tend to recommend students go out and get that first degree in a science and then go on to expand from there.
Good advice. Well, Libby, where can people follow you online?
I'm on Twitter. You can follow me on Twitter. I have a group webpage that I update almost daily with what's going on in my group, as well as things like publications, etc. So those are two good places that you can follow me. On Twitter, I'm at @mosbarnes.
Awesome. We'll have links to both in the show notes. Thank you so much for taking the time to come on and share your expertise.
No problem. Thank you, Kyle.
That concludes another installment of Data Skeptic Time Series. Thanks to our sponsors this week, Oval Edge. Our guest today was Elizabeth Barnes. Myself, Claudia Armbruster, Associate Producer. Vanessa Bly does guest coordination. And our host, Kyle Polich.